Swayam Prabha. Digital India. Educated India.
I welcome you all to lecture number 20 on the topic vapor compression cycle. Before seeing the contents of this presentation, let us have a quick recap on the topic which we have discussed in the previous lecture. We have started the previous lecture with the various hygrometric processes, sensible heating, sensible cooling, humidification, dehumidification, combination of sensible heating and humidification, then combination of the second and the fourth process, that is cooling and dehumidification, evaporative cooling, chemical dehumidification and mixing process. So, if you see the individual processes, sensible heating, it causes the dry bulb temperature to increase without any change in the humidity. Similarly, cooling also no change in the humidity, specific humidity, but the temperature at 2 is less than temperature at 1. Then humidification, the process is perpendicular to the x-axis or parallel to y-axis. Specific humidity after humidification is more than the specific humidity before humidification. It is a process in which moisture is added to the air. If you remove the moisture from the air, it becomes, without any change in the dry bulb temperature, it becomes dehumidification process. So, W2 is less than W1. Then we have seen heating and humidification, where both dry bulb temperature and specific humidity increases, and cooling and dehumidification process just opposite to heating and humidification, where both dry bulb temperature and specific humidity decreases. Then we have seen evaporative cooling process and chemical humidification process, where the enthalpy at 1 is equal to enthalpy at 2, that is H1 is equal to H2. It is the enthalpy remains constant. In case of evaporative cooling process, what is happening is it is the air for the water to evaporate, because it uses air and water. For the water to evaporate, it takes the heat from the air. So, the latent heat for evaporation is supplied by the sensible heat of the air. Sensible heat lost by the air is equal to latent heat gained by the water. So, the dry bulb temperature of the air comes down, whereas in case of chemical dehumidification process, that is also similar to during that process also the enthalpy remains constant, but that is done by using some chemicals. And in mixing process, two air streams mix, that is one air stream 1 and stream 2 mixes, and we get a resultant mixture. That dry bulb temperature and that enthalpy will lie between state point 1 and 2. So, it will not be less than state point 1 or it will not be more than state point 2. So, using stream 1 we can fix point number 1 if we know any two property like relative humidity and dry bulb temperature. I am just referring to the numerical which we solved in the previous lecture, that is the third numerical question. Using dry bulb temperature 1 and relative humidity, we can find state point 1. Similarly, using the dry bulb temperature 2 and relative humidity, we can find state point 2. So, using mass balance we can find M3, that is M1 plus M2 equal to M3. Then apply the energy balance, M1 into enthalpy at 1 plus M2 into enthalpy at 2, because these two are entering stream. So, the arrow marks are same, that is energy in is equal to energy out, that is enthalpy of the leaving stream, mass into enthalpy of the leaving stream. So, that is the energy balance. So, using this equation we can find H3. Once we know H3, just do a reverse process. From H3, fix the point H3, draw a line parallel to the wet bulb temperature line, then up to the point where it intersects the process 1 to 2. So, what happens, this enthalpy line from 3 will touch the process 1 to 2. So, that intersection point is state point 3. So, that is the condition of air after mixing process. Now, let us move to the contents of this lecture. Introduction, reversed Carnot cycle, the ideal vapor compression cycle, and two numerical questions which I will be solving. So, if you recollect the second law of thermodynamics, there are two statements. One is Kelvin-Planck statement and another one is the Clausius statement. Kelvin-Planck statement says that for a heat engine to operate, there should be two thermal energy reservoir. That means source should be there and also sink should be there. Both source and sink should be there. Engine cannot produce net work in a cycle, thermodynamic cycle, by exchanging heat with a single reservoir. So that is Kelvin-Planck statement. Clausius statement, if you want to transfer the heat from low temperature region to high temperature region, that is possible only with the aid of some external source, So that we have applied that one for a refrigerator and a heat pump. In case of a refrigerator, the desired effect is the amount of cooling which is produced, refrigerating effect, that is the desired output. Whereas in case of heat pump, how much heat has been extracted and it has been rejected to this one. So that is the desired effect of a heat pump. The COP of a heat pump is equal to COP of refrigerator plus 1. So we have done this small derivation also in one of the earlier lectures. So the Clausius statement of the second law of thermodynamics, the desired output is the heat removed from the cold medium, so from the space where we want cooling. And in heat pump, the desired output is the heat supplied to the warm medium. So this is the schematic of a reversed Carnot cycle. So just to recollect what is the Carnot cycle, it consists of two isothermal process and two isentropic process. So there is one heat addition, one heat rejection, both takes place at isothermal, constant temperature, and two isentropic process. As I have told before, all the power producing cycles will have the arrow marks in the clockwise direction, and the power absorbing cycle will have the arrow marks in the anti-clockwise direction. So here this is the reversed Carnot cycle. We have the compressor, then condenser, turbine and evaporator. Okay. So since it is a reverse cycle, the arrow marks, it is in the anti-clockwise. Otherwise, if you take the Carnot cycle, which is the most efficient cycle for producing power, it's a power producing one, where the engine is this one. So you reverse the process of the Carnot cycle, it is the reversed Carnot cycle. So the arrow marks are in the anti-clockwise direction. This forms the basis for the ideal refrigeration cycle. So here if you see the reverse Carnot cycle, this is compression, isentropic compression. As I said, whether it's a Carnot cycle or reverse Carnot cycle, it consists of two isothermal. These two are the isothermal process. I have plotted this process on a temperature entropy plot. 1 to 2 is isentropic process. Similarly, 3 to 4 is isentropic expansion. This is compression. 2 to 3 is, okay, so 2 to 3 is this process which takes place in the condenser, that is heat rejection, and 4 to 1 is heat addition. So this is like heat supplied and this is heat rejected, heat supplied and heat rejected. If you recollect the notation which I used while I was explaining the Clausius statement, the refrigerator heat pump, QH and QL, QH and QL. For a refrigerator, the desired output is how much heat is extracted from the low temperature region. So that is QL or TL, TL by TH minus TL. For a heat pump, the desired output is the how much heat has been transferred to the high temperature region. So that is QH. So or in T, if it is a Carnot one, so we can use QH as for a reversible one. So QH is replaced by TH, QL is replaced by TL. So TH divided by the temperature difference between the high temperature region and the low temperature region. So here this is the amount of heat supplied and this is the amount of heat rejected. So this is these 2 to 3 and 4 to 1 are isothermal process. So this is the process which are as per the reversed Carnot cycle. So two perfect reversible adiabatic process, isentropic process, where entropy at 1 is equal to entropy at 2. Similarly, entropy at 3 equal to entropy at 4. Temperature is T1 is equal to T4 and T2 equal to T3. So let me write it here, entropy at 1 is equal to entropy at 2. Okay, for your understanding, this is entropy at 3 is equal to entropy at 4. And if you extend this line, T4 is equal to T1 and T3 equal to T2. Okay, now you compare this process. So this is the reverse Carnot cycle, compressor, condenser, turbine and evaporator. Now here I am comparing, just compare this reversed Carnot cycle with the schematic of the ideal vapor compression system or vapor compression cycle. I have compressor, condenser, the turbine is replaced by an expansion device. The turbine is replaced by an expansion device, and of course I have the evaporator. So these three components are exactly same, only the turbine, instead of turbine I have like a expansion device. Okay. So compared to the ideal the reverse Carnot cycle, the turbine is replaced by an expansion device. So this is the temperature entropy diagram, and if you see the actual one, there is a deviation between the reverse Carnot cycle and the deviation in the process between the reverse Carnot cycle and the ideal vapor compression cycle, 1 to 2 is isentropy compression. So here also it is fine, here 1 to 2 is isentropy compression, 2 to 3 is isothermal. Okay. So 2 to temperature entropy diagram. So 1 to 2 is isentropy compression, then we have 2 to 3 is heat rejection, 3 to 4 is expansion, and 4 to 1 is evaporation process. So this is condenser, this is evaporator, this is condenser. So compressor is a device which requires electrical energy, so it is work is done on the system. Condenser rejects heat, so the arrow mark is pointed towards outside, and this is the heat addition process. Heat is extracted from the space where we want cooling, so the arrow mark is pointed towards this one. Now let me explain this process. The refrigerant which comes out of the evaporator, it is low pressure, low temperature. So it is leaving the evaporator at low pressure and temperature. In an ideal case, we assume there is no pressure drop, there is no losses. So whatever the temperature and pressure at which the refrigerant leaves the evaporator, it will be in the same condition when it enters the compressor. So that is why we use only one state, but in actual case there will be pressure drop, there will be losses. So the temperature and pressure at this point may not be here, same thing, and similarly the pressure and temperature at this point will not be equal to the pressure and temperature at this point. Now the compressor is compressing the refrigerant, so it pressure and increases, it increases the pressure from evaporator pressure to condenser pressure. Again this system or this cycle operates two pressure level, it is a two pressure level system where the evaporator is at low pressure and the condenser is at high pressure. So if you want to transfer the refrigerant from a low pressure region to high pressure region without the aid of an external source, it is not possible. The Clausius statement is violated as per the second law of thermodynamics. So the external source, the external device which is used in this case is compressor. So this raises the pressure and the temperature from evaporator to condenser. So the condition of the refrigerant at state point 2 is high pressure and high temperature, and so here it is high pressure, high temperature, refrigerant vapor. Refrigerant is the working substance which is used in the refrigeration or air conditioning application. So high pressure and high temperature, refrigerant vapor. Okay. So here it is low pressure, low temperature, refrigerant vapor. Compressors are designed for compressing the gases and not for liquid. So here also it is vapor, here also it is vapor. Okay. So there is no change. So let me resist. So the pressure. Now the process which takes place in the condenser is a phase change process where the high pressure, high temperature vapor, it converts into liquid. So here I have high pressure, refrigerant liquid, refrigerant liquid. So there is a phase change from vapor to liquid, and during the process the latent heat is this one. So it is removed by the coolant. Normally in case of a small capacity systems, air is used to remove the heat. Air is used to remove the heat. So, high pressure refrigerant liquid comes. Now, this liquid is at high pressure, but the evaporator is operated at low pressure. So, what happens is there should be a device which has to be incorporated between the condenser and the evaporator in order to reduce the pressure, So, the process which takes place in the expansion device is throttling process. Enthalpy at 3 is equal to enthalpy at 4. Enthalpy at 3 at 4 which we can easily infer from the pH diagram, pressure enthalpy diagram. Okay. On a temperature entropy plot, the process 3 to 4 is a inclined line, it is not a perpendicular line, whereas on a pressure enthalpy chart or a pressure enthalpy plot, the throttling process will be a line perpendicular to the x axis. So, now this expansion device, it could be a capillary tube or it could be a valve. So, it will reduce the pressure of the refrigerant from condenser pressure to evaporator pressure. Now, here it is low pressure liquid refrigerant, low pressure refrigerant liquid, low pressure liquid. So, it may, of course, the temperature also will be low only, So, what happens is during this process of throttling, sometimes there are chances that some of the liquid refrigerant, while this is like a flashing process, so it gets converted into vapor, maybe 5% or less than 10%, remaining it will be in liquid only. There are chances that here it will be in two phase, like 90% liquid, maybe 10% vapor due to the flashing of the liquid, because there is a sudden reduction in the pressure from the condenser pressure to evaporator pressure. So, once the refrigerant enters the evaporator, so it takes the heat. Suppose if you want to cool the air, so it takes the heat from the air, or suppose if you want to store some items at a low temperatures, so it takes the heat from the food items or whatever it is, thereby it becomes vaporized. So, for the vaporization of the refrigerant, it needs heat. So, that heat is sensible heat is taken from the medium which has to be cooled, So, thereby the liquid refrigerant, it changes into again vapor, and the process continues. If you look at this process, right side the compressor is there, left side there is an expansion device. On the right side we are increasing the pressure and temperature, on the left side the pressure is reduced. So, why we have to do this one? For raising the pressure, for increasing the pressure, the compressor is used, and compressor is not a device which operates without electrical energy. It requires huge amount of electrical energy. It is not like a fan, small fan or a small pump. So, it is a device which absorbs, which requires large amount of electrical energy, and the power consumption depends upon the cooling capacity. So, according to the compressor, compressor power requirement, compressor capacity. So, of course, when the cooling capacity changes, the compressor specification also will change. So, now on the right side we are increasing the pressure, on the left side again we are decreasing the pressure. So, why we have to increase and why we have to decrease? If we do not increase the pressure by using a compressor, if we do not raise the pressure from evaporator pressure to condenser pressure, then condensation will not take place. By increasing the pressure and temperature, so then only the heat transfer will be there in this one. So, heat will be transferred from the high temperature this region to the sink, sink here is the air. Similarly, if I do not reduce the pressure on the left side, that is process 3 to 4, then evaporation will not take place. Of course, we are not spending any electrical energy to reduce the pressure of the refrigerant from condenser pressure to evaporator pressure, but lot of energy and a lot of cost are involved when we want to increase the pressure of the refrigerant from evaporator pressure to condenser pressure. So, let me write it here. Here the low pressure is evaporator, high pressure is condenser, once again let me repeat. The purpose of increasing the pressure with the help of the compressor, if we do not increase this one, then condensation will not take place. Condensation will not take place. Suppose if this temperature is less than the outside sink temperature, the air temperature, ambient. So, obviously, the heat will flow from the air to the condenser, not the other way. Similarly, if you do not reduce the pressure during the process 3 to 4 on the left side, which as per the schematic, evaporation will not take place. The COP of the system is evaluated in term, it is the ratio of how much cooling is produced in the evaporator divided by the power required to drive the compressor. Theoretically or in ideal condition, if you see the evaporator heat load, that is the cooling capacity of the evaporator, and the work of compression compression, okay, because we use letter C for condenser. So, for work of compression I will use CO. CO refers to compressor and C refers to condenser. So, these two quantities will be equal to the heat rejected during the condensation and from the condenser during the condensation process. QE plus WCO will be theoretically equal to QC. Okay, so this is here. So, here also let me write, this is the work of compression. So, this is the refrigerating effect. The refrigerating effect is produced during the process 4 to 1. So, the enthalpy difference is H1 minus H4 into mass flow rate of the refrigerant M into M dot R mass flow rate of the refrigerant, okay, mass flow rate of the refrigerant, and the work of compression is, so 1 to 2 is isentropic compression, 2 to 3 is, if you see this diagram, 2 to 3 is like a constant temperature from here this one. So, this is like a superheated condition, 2 is in superheated condition, this is saturated vapor, 3 is in saturated liquid. So, at the entry of the condenser the refrigerant is in vapor, and at the exit of the condenser it is in liquid. So, this is vapor region, this is liquid region, okay. So, this is saturated vapor curve. Let me explain, let me write saturated vapor curve, saturated vapor line, and this is saturated liquid line, saturated liquid line. So, the region between the saturated liquid line and saturated vapor line is in two phase region, it is a mixture of liquid and vapor, okay, and this is subcooled region and this is superheated region. So, this state point 2 as per this TS diagram, it is the condition of the refrigerant is in superheated. So, the refrigerant initially it is at saturated condition, that is the temperature refrigerant which is coming from the evaporator, which is entering, this is the inlet of the evaporator, this is the outlet of the evaporator. Then we have the heat rejection process, then 3 to 4 is throttling, this is throttling process on a TS diagram, and 4 to 1 is isothermal heat addition process. So, this is a line perpendicular to the y axis. So, the COP of the system is how much heat the cooling is produced here, desired effect QE by the work of compression is this one WCO. So, M dot R and the M dot R will get cancelled. So, it is H1 minus H4 divided by H2 minus H1. The enthalpy difference during the heat addition process divided by the enthalpy difference during the compression process is the COP of the system. So, with this background, let us solve two numerical. In the first numerical question, the values are given, the enthalpy values are given. So, we will not be referring the refrigerant table. In the second numerical question, I will explain by taking the values, the enthalpy values, the specific heat values from the corresponding refrigerant table. A standard vapor compression refrigeration cycle operating with a condenser temperature of 35 degrees centigrade. So, condenser temperature, there is a high temperature is given 35 and the evaporator is the low temperature minus 10, develops 15 kilowatt of cooling. So, the cooling capacity of the system is given. So, the evaporator heat load is 15 kilowatt. The pressure enthalpy diagram shows the enthalpy at various state. So, this is also given, this is also given. This is the pressure enthalpy diagram, pressure is in kilopascal, enthalpy is in kilojoule per kg. So, let me emphasize again, I said process 3 to 4 is constant enthalpy process, isenthalpic process. Enthalpy at 3 is equal to enthalpy at 4, enthalpy at 3 is equal to enthalpy at 4. So, this is the, there is again there is some, so 1 to 2 is isentropic compression. So, this is where, this is the process during which power is required to drive the compressor. 2 to 3 is heat rejection process, okay, heat rejection process, that is heat rejected by the condenser. Let me draw this QC and this is QE, this is QE. 3 to 4 is isenthalpic process, enthalpy at 3 is equal to enthalpy at 4. We can see enthalpy at 3 is equal to enthalpy at 4, enthalpy at 4. So, these are all the values. The enthalpy at 1 is given, this is state point 1, 400, enthalpy at 2 is given, enthalpy at 3 and enthalpy at 4. If you look at the COP formula, there are 4 enthalpies, H1, H2, of course H4. H4 we can find only if we know H3, H3 equal to H4, H3 is equal to H4. Okay, so enthalpy at 3 is equal to, let me write it here, enthalpy at 3 is equal to enthalpy at 4. Okay, so here also let me write it, enthalpy at 3 is equal to enthalpy at 4, that is expansion process, isenthalpic process. So, once we know the enthalpy at 3, we can that is equal to the enthalpy at 4. So, once we know 4 enthalpy, we can find out the COP, we can find out with the 2 enthalpy, we can find out what is the cooling capacity. Of course, for this problem the cooling capacity is given. If we know 2 H1 and H2, we can find out how much power is required to drive the compressor in terms of kilojoule per kg. Once we know the mass flow rate, we can find out the power in terms of kilowatt. And also once we know the enthalpy 2 and 3, we can find out the heat rejected in the condenser. So, let us write the given data. The condenser temperature is given 35, given data, okay. Condenser temperature, that is the height, of course here also compared to the evaporator temperature it is high. Anyway, let us write Tc, which is equal to 35 degrees centigrade. The evaporator temperature is given as minus 10 degrees centigrade. Okay, and now we can read out this enthalpy. Enthalpy from 1, from this pH chart with values are given in the problem. So, we are not taking the values from the table. H1 is 400, H2 is 475. Let me write this one. From pH diagram, from the given pressure H diagram, from the pressure enthalpy diagram, H1 is equal to 400 kilojoule per kg, H2 is equal to 475 kilojoule per kg. And what is the enthalpy at 3? Enthalpy at 3 equal to 4 equal to 250. 250. The corresponding pressures are given. 400 kilopascal and 650 kilopascal. Okay. Enthalpy at 3 is equal to, see, this is from the given pH diagram. Normally these values will not be given. So, this is one of the question which has been asked in the gate examination, previous gate examination. So, H3 is equal to, what is that value? 250. 250 kilojoule per kg. So, these 3 are given. Now, we have to just directly substitute in the formula. Okay. So, there is one, the pressure isentropic efficiency of the compressor is given 75%. So, we have to find out the power required to drive the compressor, WC naught. So, power required to find the power required to drive the compressor, So, that means we have to find out WC naught or actual, because the isentropic efficiency is given. So, okay, power required to drive the compressor, actual, how much? Okay, so let me write this one here. Power required to drive the compressor, actual. Okay. So, since the cooling capacity is given as 15 kilowatt, so that also is given. QE is equal to 15 kilowatt. You can use small letter e or capital letter E. Okay. So, now QE is equal to, if you write the formula, mass flow of the refrigerant circulated into H1 minus H4. So, using this one, I can find out how much quantity of refrigerant is H1 minus H4. This is given from the, this we can take the value from the pH diagram and so using this one, so you can find out the mass flow rate of the refrigerant circulated. So it is in, this is mass flow rate per kg per second, okay, kg per second. This is in kilowatts, this is in kilojoule per kg, okay. So kilojoule, kilowatts can be written as kilojoules per second. Right side we have the quantity in kilojoule per kg. So kilojoule and kilojoule will get cancel, we will get the answer in terms of kilograms per second. So m dot r is, m dot r, this is m dot r, okay, m dot r is 0.1 kg per second, 0.1 kg per second. So this is the mass flow rate of this refrigerant. So we should know this one, then only we can find out the power required to drive the compressor, that is m dot r into delta H. Now I am finding the isentropic work done, that is WC naught. So this is nothing but work of compression isentropic, okay, isentropic, work of compression for the isentropic. So this is nothing but work of compression of the isentropic, just for your understanding, because the terms which are used are slightly different, sometimes it will be confusing. This is the isentropic work done, because we have given the isentropic this one. So we are calculating the, like the theoretical work done, work done on the compressor. So that is m dot r, okay. So this is WCO. When we say when we put WCO isentropic, it is nothing but WCO only. For actual, I will be using the word actual. So now work of compression or work of compression for both are same, isentropic is equal to mass flow rate of the refrigerant, and compression takes place during this process, 1 to 2, during this process, okay. So this is during this process, 1 to 2 is isentropic compression. So enthalpy at 2 minus enthalpy at 1, okay. So this enthalpy at 2 minus enthalpy at 1, okay. So this is equal to H2 minus H1. If we don't know m dot r, we cannot find out WCO in terms of kilowatt. Of course, we can find in terms of kilojoule per kg. So all these values are known. So substitute, we will get 7.5 kilowatt, 7.5 kilowatt. This is the theoretical power requirement for the compressor, but the efficiency of the compressor is not 100%. Okay, it is given the isentropic efficiency of the compressor is 75%. That means the actual power consumption will be more. When you divide the isentropic compressor, the power requirement of the compressor for the isentropic process divided by the actual, this one, it will be more. So I will be using this formula. The compressor efficiency is isentropic work done by actual work done. Efficiency of the compressor is equal to isentropic by compressor actual. Now this is given 75%, this we have found out 7.5 kilowatt. So using this one, find out the actual power compression, okay. So that will be, this is isentropic work done by the compressor divided by the efficiency. For if you want to find out the actual power requirement for the compressor, the efficiency should be divided. In case of a turbine, it should be multiplied. For a power producing device, multiply the efficiency, given efficiency, to find out the actual one, and for a power absorbing device, divide the value by the given efficiency. So this is equal to 10 kilowatt. So the actual requirement is 10 kilowatt, but the theoretical one is 7.5 kilowatt. So there is a difference of 2.5 kilowatt. So we have been asked to find out the actual power requirement, Okay, so let me write this one clearly, so that this is actual. So that completes the problem. Now let us move to the second numerical. A refrigerator uses R134A tetrafluoroethane as the working fluid and operates on an ideal vapor compression refrigeration cycle between -18 and 32 degrees centigrade. That means evaporator temperature is -18, condenser temperature is 32. So let me draw this. This is the given data. Evaporator temperature is -18 degrees centigrade. Condenser temperature is, I think it is 30. let me take the value 32, okay, 32 degrees centigrade. Okay. So, this is minus 18. So, this is what minus 18, minus 18 degrees centigrade, and this is 32. Plotted. 1 to 2 is isentropic compression, then we have the heat rejection, constant temperature, there is some amount of cooling takes place from 2 to 2 dash, then from 2 dash to 3 is constant temperature heat rejection, then 3 to 4 is isenthalpic process, and 4 to 1 is constant temperature or constant pressure isothermal process heat addition. So, this is when I say this temperature is minus 18, T4 is equal to T1 equal to minus 18. Okay. So, I will be using, so this is nothing but T4 equal to T1. So, let me draw the diagram again here. Okay. So, this is 1 to 2, then there is little amount of cooling, then let me take this point as 2 dash, because we need to find out the property at this one. This is 2 to 3, then 3 to 4, 4 to 1. This is expansion process 3 to 4, and this is QE, this is QC. So, the y axis is temperature, this is x. So, this is given, this is minus 18 degrees centigrade, this is 32 degrees centigrade. So, for easy reference I am drawing the diagram here. Okay. So, now here the enthalpy values are not given, we should know the enthalpy at 1, 2, 3. Once we know the enthalpy at 3, that is equal to enthalpy at 4, okay, isenthalpic process. So, this difference is the theoretical power requirement for the compressor WCO. Now, if you see this temperature T2, this is the condenser temperature, T2 dash and T3 are same. So, this also I can write it as T2 dash is equal to T3 from the diagram. So, let us quickly solve this one because we have to take the properties. Now, if you see the condition of refrigerant 1, look at this diagram. The refrigerant 1, it is in saturated vapor line. So, let us take state point 1. At state 1, refrigerant is in, or we can write it state 1, it is refrigerant is in saturated vapor. This is saturated vapor curve, this is saturated liquid curve, saturated vapor. That means dryness fraction is 1. So, if you apply in the formula H1 is equal to HF1 plus X1 into HFG1, because H1 is 1, the HF term will get cancelled. So, H1 equal to H2. So, therefore, enthalpy at 1 is equal to enthalpy at the gaseous enthalpy at this temperature. What is this temperature? Minus 18 degrees centigrade. And the refrigerant which we are using is R134A. R134A, that is the refrigerant gas which is used, which is the working fluid, So, from refrigerant table R134 table corresponding to a temperature of minus 18, we can directly read the enthalpy corresponding to Hg value, because dryness fraction is 1. So, it is in the refrigerant, the condition, the state point 1 is in saturated, it is lying on the saturated vapor line. Okay. So, from so this is from R134A table, from R134A table. So, what is this value? H1 is equal to, because this is the first problem. So, this is the R134A table, okay. So, this is the R134A table. There are 2 pages. In the first page, the first column is temperature, this is temperature, okay. This is pressure. So, the temperatures are given, okay, if temperature, okay.
So, the temperatures are given as minus 18, the low. So, this is minus 18, and in the second page, in the first page, that the properties are given from minus 60 to 22, and from the second page it is given from plus 24 to up to 80. Okay, so only two tables are there. Unlike steam table, there is no steam table 1, 2, 3, 4, 5. So, here the values are given for saturated liquid and saturated vapor. If it is for superheated condition or subcooled condition, we have to use empirical relation and find out for the values for superheated or subcooled regions. So, now corresponding to 0.18, so we can find out the pressure also. The saturation pressure is 1.44 bar, 1.44 bar. Now, enthalpy at 1 is equal to the this is the enthalpy one, this is the enthalpy. Okay, so this is the enthalpy, this is enthalpy. Okay. Now, I will read the Hg value directly corresponding to minus 18. This is Hg, and this is Hf. Hf will be, I will be using later. So, the corresponding to minus 18, the value is 387.89, 387.89. So, that is what I have written here, 387.89, I have round off 387.9. 387.89 kilojoule per kg. Similarly, read out the enthalpy value. What is the entropy value at this point? At 1, H1 equal to Hg, S1 is equal to Sg, S1 equal to Sg. These two are same. Okay. How to find S1 equal to Sg? S1 equal to Sf1 plus x1 into Sfg1. Sfg1 can be written as Sg1 minus Sf1. Okay. So, because the dryness fraction is 1, it is a saturated vapor, the Sf term will get cancelled. So, S1 equal to Sg, Sg1 and H1 equal to Hg1. Okay. So, from this table S1 is equal to Sg1 is equal to, from the same table, this is Sg, and this is Sf. Okay. So, corresponding to minus 18, I have taken two values, one is Hg value and one is Sg value, because there are multiple state points 1, 2, 3, 4. If we write Hg, Sg, it will be confusing because there are two different pressure, temperatures and pressures. So, we have to write Hg1 and Sg1. Sg1 is 1.7399, that is what I have written here, 1.7399, 1.7399 kilojoule per kg Kelvin. Okay, so these to be this is also at minus 18 degrees centigrade from the R134A table, So, now at state point 1, I have found the enthalpy of the saturated vapor and entropy of the saturated vapor. If you look at the diagram, here, 2 is in superheated condition. Okay, state point 2 is superheated state. I cannot take the enthalpy value directly from the table because those property values are for saturated liquid and vapor. It is not for superheated condition. So, how to find this one? But I can find out the enthalpy at 2 dash, because 2 dash is lying on the saturated vapor corresponding to condenser temperature of 32. 1 is also lying on saturated vapor, but at 1 the temperature is minus 18, at 2 dash the temperature is 32. Of course, 2 is lying in the superheated region. Now, what I am doing is, okay, so I am going to find out the value of this one. I am going to use the isentropic process S1 equal to S2. Okay, 1 to 2 is isentropic process. Okay, 1 to 2 is isentropic compression. 1 to 2 is isentropic compression process. Therefore, entropy at 1 is equal to entropy at 2. Okay, so this, if you extend this one, S1 is equal to S2. Entropy at 1 is equal to entropy at 2, isentropic compression process. Okay. Now that is what I have written here. Okay. Using this formula S2 minus S2 dash is equal to Cp of vapor into ln of T2 by T2 dash. Now I have to find out this entropy, this temperature, sorry. We do not know what is the temperature at state point 2, this is not known. We do not know this temperature at state point 2. T2 is unknown, T2 is not known. We know only the temperature at the evaporator, that is minus 18. We know the temperature in the condenser, that is plus 32. So T2 is above T2 dash, so it will be more than 32, it will be more than 32. Okay. So now I am going to read the values corresponding to T2 dash. What is the temperature at T2 dash? Temperature at T2 dash, the temperature at T2 dash and T or T3 are same, that is equal to Tc, that is equal to Tc. So from steam table at T2 dash is equal to T3 is equal to 32 degrees centigrade. From R134A table, find out the value of enthalpy at H2 dash. What is the value of enthalpy dash? Enthalpy at H2 dash, that is equal to vapor enthalpy only, because point 2 dash is also lying in saturated vapor line. So H2 corresponding to 32, okay, corresponding to 32. So 32 is, it is in, this is temperature, okay, this is temperature. So I am going to corresponding to 32 is here, this is 32, this is Hg, okay, this is Hg. I am going to take the enthalpy value 4, which is equal to 415.9. Okay. So that is what I have written here, 415.9, 415.9, but I want the value of at H2, not H2 dash. So for which I am using H2 dash enthalpy also, okay. So kilojoule per kg. Okay. So now, and also we have to take the Cp of vapor, and also we have to take the Cp of vapor. So before that, let us take this process, isentropic process S1 equal to S2. Now there is a relation between change in entropy and temperature, ratio T2 by T2 dash. So before that we have to take this value also. Okay. So from let us take this value later, we will take this entropy value. First we will take the entropy value. Okay, let us take this also, H2 dash is equal to Hg is equal to 415.9 kilojoule per kg. Similarly, entropy at 2 dash also I am taking, that is okay. So if you take the table corresponding to 32, Sg value, this is Sg value 1.7142. 1.7142 kilojoule per kg Kelvin. Okay. So use this formula, S1 minus S2 dash is equal to Cp of vapor into ln of T2 by T2 dash. S1 minus S2 dash is equal to Cp of vapor into ln of T2 by T2 dash. This is a standard thermodynamic equation, okay, relation. So and corresponding to 32 also, now here if you see this formula, this is Cp of vapor. How to take the Cp of vapor? So that also can be taken from the refrigerant table corresponding to 32. This is specific heat, this is specific heat, this is Cp value, this is for liquid and this is for vapor, this is for liquid, this is for vapor. So corresponding to 32, I will be taking Cp of vapor 1.058. Okay. So from the corresponding to 32 only I am taking these values, H2 dash that is equal to Hg, S2 dash I will be using it later, because my aim is to find out what is the temperature at 2, what is the temperature at 2. So Cp of vapor is equal to, okay, Cp of vapor is equal to 1.058, 1.058. See 1.058, this is the Cp of vapor, 1.058 kilojoule per kg Kelvin. So, these three values have to be taken for this temperature. Now, entropy at 1 we know, entropy at 1 we know, we have found out, okay, minus S2 dash, entropy at 2 dash I have found. So, this is known, Cp of vapor is known. Generally, the properties to be taken at average temperature, because we do not know the temperature T2, I am taking the Cp value corresponding to T2 dash. The only unknown is this one, So, substitute the value and find out the temperature T2. So, if you see the calculation, the T2 temperature is 39.5 degree centigrade, close to 40, 39.5 degree centigrade. So, this is the temperature here. So, T2 is above T2 dash. So, this is temperature at 2 equal to 39.5 degree centigrade, which is more than 32. Once we find the T2 temperature, okay, I am going to find out the enthalpy at 2. What is the enthalpy at 2? This is superheated enthalpy. So, there is a formula, superheated enthalpy is equal to saturated enthalpy H2 dash plus Cp of vapor into T2 minus T2 dash into delta T. There is a formula. If this is this superheated enthalpy, this is superheated enthalpy, enthalpy at superheated enthalpy at point state 2, at state 2. Okay, so, this is very, very important. H2 equal to H2 dash plus Cp. H2 dash I have found out here. Now, the Cp of vapor we have to find out for these Cp of vapor, because I know T2 and T2 dash. The correct method to find out the property is average temperature, but here I do not know T2 temperature. So, I took the Cp value for T2 dash. Okay, so, I took it at T2 dash, but here Cp of vapor is equal to, Cp of vapor should be taken at average temperature, Cp of vapor should be taken at average temperature. So, T2 is 32, T2 dash is 39.5, approximately 40, 40 plus 32 by 2. So, this is 32 plus 39.5 by 2. So, Cp of vapor should be determined. Okay. If you see this one, approximately 39.5 is 40, 40 plus 32 is 72 by 2, that is 36. So, corresponding to 36 only, I have taken the Cp of vapor at this temperature. This is very, very important. So, corresponding to 36, Cp of vapor is this last column 1.088. So, that is what I have got here. So, let me quickly go through it. Cp of vapor at, so this is equal to 36 degree centigrade, at 36 degree centigrade from steam table 1.088 kilojoule per kg Kelvin. Now, substitute this here, find out the enthalpy. Now, only I am getting the enthalpy at state point 2. If you calculate the value 424.1 kilojoule per kg. Now, I know enthalpy at 1, okay, enthalpy at 1, enthalpy at 2 I have calculated. To find out the enthalpy at 2, we should know enthalpy at 2 dash, which can be found directly corresponding to temperature T2, saturated vapor enthalpy. The Cp of vapor we should be take from the average temperature. This is very important. In order to know this T2, we should use this relation S1 minus S2 dash is equal to Cp. How I am writing S1 and S1 is equal to S2, S1 is equal to S2, entropy at 1 is equal to entropy at 2. Now, to find out the enthalpy at 3, 3 is lying in saturated liquid region. So, state 3, let me quickly write saturated liquid. So, H3 is equal to, okay, H3 is equal to What is the temperature at 3? Temperature at 3 is 32. H3 is equal to, okay, let me write it clearly because letters are not clear. H3 is equal to liquid enthalpy at T3 is equal to 32. So, go to the table corresponding to 32, liquid enthalpy is this one, 244.55, 244.55. So, that is what I have written here, 244.55, okay. So, 244.55. So, therefore, H3 is equal to 244.5 kilojoule per kg. This is equal to H4 because H3 equal to H4. Once I know all the 4 enthalpy, okay. Rate of heat removal from the refrigerator, Q equal to MR into mass flow rate is given, okay, mass flow rate is given. I think mass flow rate, it is given as 0.05 kg per second. So, let me write it here, mass flow rate of the refrigerant is also given 0.05 kg per second, okay. So, use this formula to calculate QE, power required to drive the compressor, heat rejection, COP of the refrigerator, energy balance is cooling capacity plus work done on the compressor, work of compression. If you add, you are getting 8.98 when we calculate the heat rejected by the condenser. So, it is a perfect energy balance, QE plus WCO equal to heat rejected by the compressor, okay. So, to summarize, we have seen the reversed Carnot cycle which forms the basis for the ideal refrigeration cycle, where the expansion process, the turbine is replaced by an expansion device, whereas the other processes, compression, heat rejection and heat addition are same, that is evaporation and condensation. So, with this let me conclude the lecture number 20. Thank you.
Hello and welcome to this piece of literary snippet. We usually know William Shakespeare as the most revered figure in the history of English literature. But we often tend to forget that he has also been one of the most hated figures in literature. And here I am not talking only about those boys and girls who have to memorize long sections from Macbeth or King Lear or Julius Caesar before they can go and sit for their school or college exams. But I am also talking about people who are themselves quite famous authors. Tolstoy, for instance, considered the writings of Shakespeare to be, and I quote, crude, immoral, vulgar and senseless. George Bernard Shaw absolutely loathed Shakespeare, as he did Homer. But perhaps no other criticism about Shakespeare is more damaging than the one which says that Shakespeare is a marvelous storyteller, provided someone has told him the story earlier. Now, this piece of criticism is particularly damaging because it is true. None of Shakespeare's plays contain any original story whatsoever. They are all written using pre-existing materials, pre-existing stories. Now, does that diminish the stature of Shakespeare as a dramatist? Well, I'll leave that for you to decide. See you in the next episode of Literary Snippets.